This is a presentation on aerodynamic design methods for single element wings for motorsport use. For motorsport, drag is less important than lift. Designing a wing can be as simple as choosing a high lift profile that you found on the internet that meets your desired specification, say from airfoiltools.com. Creating a new profile from scratch is a lot more complicated with two main approaches: direct design and inverse design procedures. However, in the real world, the wing is finite and more than just a profile that adds to the process. Typically, adding an endplate is required to gain back some of the inherent losses. This is due to the interaction between the top and bottom of the finite wings profile. Why and how this interaction happens will be addressed here. Just choosing a high lift profile is a good start and good enough for amateur racing series. The next step would be to implement a direct design process that would take a series of profiles and analyze them in software. There are two programs among others that someone could use for this level of design: OpenFoam and Xfoil. OpenFoam could run basic wing profiles even with endplates on a laptop, but you'll need a method to get the profile into the software. Xfoil, on the other hand, is lighter and provides pressure distributions quickly because it's only 2D. But because it is 2D, it is limited to the profile with a trailing edge flap. There are 3D equivalents, AVL and XFlyer 5, which is mostly for planes, but apparently you can use it for multi-element wings, but you're better off using a finite volume method based software here. However, Xfoil has one big advantage. It has the ability to use inverse design methods where the pressure plots can be altered and the wing profile adjusted to match the pressure distribution. This is an important method for profile design, and it has been used to develop a lot, if not most, high-lift wing profiles. A little background on Xfoil and the inverse design method. Liebeck in 1969 published a paper which used inverse design procedures to produce a profile to match an idealized pressure distribution. The procedure here wasn't a true inverse design method because it didn't integrate a boundary layer. Richard Epler and Dan Somers in 1980 was one of the first to develop an integrated method which was used in the profile code and adopted by NASA. There are many more subsequent methods developed since, including ones by Michael Seelig, a prominent contributor. The ones publicly accessible are 2D, like Xfoil, and are still used today. Even though processing power is far greater today than the original method was designed for, that is the 3000 point processing which was cutting edge in 1975, it is still commonly used and Xfoil has become a bit of a standard. Xfoil was first outlined in a paper published in 1989 by Mark Dreller. Xfoil, an analysis and design system for low Reynolds number airfoils. Considering this software still exists and has seen updates as late as 2013, here it will form the basis for the illustration of the inverse design concept here. I could probably fill a year's worth of full-time work just researching the development of the inverse design processes, but I'll just give it a couple of brief paragraphs. Inverse design is built on a conformal mapping method that has been well established for calculating potential flow by Kuter and Joukowsky, and explicitly outlined in the Epler paper. Adding a viscous boundary layer to the method helped gain greater accuracy to the envisaged flow model, with the addition of drag being able to be calculated. This was an important advancement because now wing profiles could be analysed without a wind tunnel and at a substantially reduced cost. Also, it would be unrealistic for the inverse design method, such that without viscous flow there would be no separation and you could generate absurd lift numbers. Going by the previous video about profiles and the Stratford pressure recovery distribution, an airfoil will have a theoretical limit as a result of the flow separation. The aim is to reach the theoretical limits for motorsport, as centre of pressure and moments that a wing has is less important than outright performance. At the heart of both Epler and Dreller's software code is the panelization method to produce numerical solutions to the conformal mapping method. This is where the profile is divided up into segments and the local circulation is calculated for the lift. Similar to how the line lifting method has been used since thin airfoil solutions were a good approximation for lift. But as circulation cannot be used for drag and the thickness profile made thin foil approximations less accurate, therefore the surface velocity became more important. Velocity can be used for calculating the boundary layer, which impact the flow separation from the adverse gradients due to the high changes in airstream velocity. How all this is linked together is nicely illustrated with the overview of Xfile design and analysis system, where you can see how the software is divided up into 4 routines. The inverse design method is implemented through the MDS routine and the MODI subroutine where the profile is modified. The program is then executed with a modified profile that the geometry is iteratively changed to match the inputted pressure distribution plot. Obviously not all pressure plots will give a result, but it is a design method to generate a usable profile. But all this is in 2 dimensions. The finite wing theory is again a step beyond the 2D wing theory, in that circulation is still fundamental to the concept and that the vorticity forms a trailing vortex sheet. The circulation is calculated along each of these horseshoe lines. There is a couple of variations of this method, Prandtl line lifting and the vortex lattice method. When in both cases the vortex is perpendicular to the chord length, it is inducing a force on the surface. However, when the vortex is running in line, it is not. This is an important concept. As the air gets closer to the edge of the wing, it changes direction, and the effect that the vortex has reduces lift. This forms the idea that the infinite wing will have a higher coefficient of lift than a finite wing. As mentioned, the lightweight vortex line lifting method is still used today in Xfoil. For 3 dimensions, there's another application from Dreller, ALV, using the vortex lattice method and their extensions of Xfoil and AVL, Xflyer 5, but these are more orientated towards aircraft design. You could probably still use them for motorsport, as I've read on forums some people have. Typically now the Navier-Stokes equations that are used in the finite volume method where the total fluid domain is calculated. This is what OpenFOAM uses, and I will be using with a chosen wing profile to demonstrate the principles of the finite wing, and how the addition of the endplates changes its performance. The chosen profile is the FX63137, which as an infinite wing had a coefficient of lift negative 0.935 at 2 degrees angle of attack. The theory says that the efficiency of the wing should be substantially reduced because the vorticities at the end will produce no lift due to them being parallel to the airstream. Subsequently, this will reduce the lift on the wing surfaces inwards from the end. Another way to put it with using the idea of pressure and momentum, pressure will leak from the high pressure volumes to the low. The pressure gradient will determine how much momentum the air has and how strong the vorticity is. Unsurprisingly, it turns out the difference between the infinite and finite wings is significant. The FX63137 as a half wing has a coefficient of negative 0.63, a reduction of almost a third. An image of the profile with the surface streams make it apparent that there is an interaction between the top and bottom of the wing. Taking a coefficient of pressure plot spanwise shows how the pressure drops at the end with a chord length of 180 mm, so the line plot at 0.16 meters is near the trailing edge. Similarly, along the chord profile, changes illustrate both the upper and lower sections of the wing leak pressure. The area in the plot represents the pressure difference along the chord, thus the less area, the less lift, shown by the line plot at 0.45 meters, which is closest to the spanwise length of 0.5 meters. One way to think of the endplates is that they're equivalent to increasing the length of the span. While it is not possible to increase the span infinitely, it is possible to gain some function back. 5 different endplates were tested in the following configurations. Endplates were added on top and below, and extended forward. Here is a plot of the lift of each endplate addition. With each addition, more lift is produced. The infinite FX63137 had a mentioned CL of negative 0.935. And the final endplate configuration had a CL of negative 0.726, a loss of 22%. However, there is a 15% gain in the addition of the endplate compared without. The spanwise plots illustrate how less the loss of pressure difference occurs. All these overlays show how much improvement there is in increasing the pressure difference. As such, the lines slowly become straighter. Chordwise, the line plots at each point along the span become less different, therefore reducing the losses in downforce. Apparent from the 3D models, the vorticities are different with each endplate modification. Comparing the first and last, the vorticity difference becomes night and day. Without any end plate, there is a tight vortex that starts very early on in the chord. The larger end plate increases the radius, and the rotation appears to start much later. Lastly, there is one observation worth noting. On the first extended end plate, there is a thing called two-wall separation. Apparently, having perpendicular walls in low pressure are more vulnerable to separation. Adding the forward extension to the end plate removes the separation. It would be a wild guess to give a reason. So in conclusion, adding more end plates the better.